I'm back, my children, and other people's children. As some of you watching this do not know me, that's okay. You don't really need to, I'm not that interesting. But you know what is interesting? The periodic table and its history and properties, which is what this video is about, conveniently for you. Let's talk first about Dmitry Mendeleev, who was the first person to organize the elements into a table back in the 1860s. Now, when I say first person, I more mean first person to like successfully do it. There's a video that I like to show my classes, the first portion of, and I'll put that in the video description on YouTube, and then in synchronous time, I will probably just straight up show it to my classes. But it's a little bit of a primer on who Dmitry Mendeleev was and what he did. And it's also a cartoon, which is like double fun. But basically, he put the periodic table in order by atomic mass in rows and then chemical properties in columns. And we used that periodic table until 1913 when Henry Moseley updated it. And what Henry Moseley did was he rearranged it so that it was in order by atomic number in rows and chemical properties in columns. Now, that is the periodic table we use today. The only difference between Moseley's periodic table and our modern one is that our modern one has more elements on it. And then the masses on the periodic table are more accurate now than they were in 1913. But otherwise, it's the same. And notice that atomic number, that would be like by the number of protons. And the reason we had to wait until 1913 to put it in order by atomic number, the reason Mendeleev could not put it in order by atomic number, is that in the 1860s, we didn't know what protons were. If you remember back in Unit 2, Rutherford discovered the nucleus, and then a couple years later, someone else discovered specifically the proton. And that was in like 1911 or 1912. So Moseley was like right on top of this. He was like, this thing, the proton, I got this. I'm going to like put my name in the history books by being the first one to cross this finish line. And then he did. But the number of protons, while that does give us a good order for the periodic table, the most fascinating thing about the periodic table is those chemical properties in the columns, because it turns out that certain elements share properties with other elements. And we call those shared properties, those elements sharing a property, we call those families. On the periodic table, those are groups or columns. So on the periodic table, when you are talking about a vertical column, we can call that a group or a family. And I like to write the word group and the word family with these like really tall G and F to help me remember that's the vertical one, versus the horizontal one is called a period. So I draw a really like horizontally long letter P to remind myself period is the horizontal, group and family are synonyms for the vertical. And when you have elements in the same family, the same group, vertically up and down, those elements share chemical properties. And so we're going to talk about 4 specific families that are kind of like the most interesting ones and also the least complicated ones, conveniently. So let's talk about groups 1, 2, 7, and 8 on the periodic table. We're going to just go straight down each group. So group 1 is called the alkali metals. And if you wanted to picture them with like a personality, they are rage-filled. They are just furious. It's sort of like the personality I would give them if I were to anthropomorphize them. The alkali metals have 1 valence electron, which contributes to some really interesting properties. So when we draw those elements with their 1 valence electron, the Lewis structure basically just have 1 dot on a side. Remember, with Lewis structures, it doesn't really matter where you start drawing the dots. You just pick a side and put your dot, and then you just keep rotating around. And it even doesn't really matter if you do clockwise or counterclockwise. So you could draw it on the right, you could draw the dot on the bottom of the element symbol, you could draw the dot on the left of the element symbol. That part's unimportant. What's important is having the right number of single dots and the right number of paired dots. And for alkali metals, there's just one single dot, and that's it. Alkali metals are soft and easy to cut. Like, they're a metal, but you can actually cut them like with one of those like crappy plastic to-go silverware knives. It's not like super easy to cut with one of those knives, but you can do it. I speak from experience. It's a metal that you could cut with one of those crappy little plastic knives. They are really soft for a metal, and they're easy to cut. But on the flip side, as a chemical property, they explode when you put them in water. And I'll, during synchronous class, probably show you a video of that if we have enough time, and I'll put a link in the YouTube comments to a video I showed during class for that as well. Okay, that's alkali metals. Let's talk about group 2, alkaline earth metals. Now, the word alkali and the word alkaline, you may notice, are very similar words, but that word for both of them basically comes from alkaline, or alkali is another word for base or basic. The same way, like acids and bases, that kind of basic, not like wearing Ugg boots at Starbucks while you are also wearing yoga pants or whatever, like not that kind of basic, but basic like acids and bases. So alkali metals, alkaline earth metals, both tend to form compounds that are bases, and that's why they are given this name alkali or alkaline, because it's a synonym for base. Alkaline earth metals are still not like super happy-go-lucky if I were to anthropomorphize them. They're not furious like the alkali metals. They're more like grumpy. They have 2 valence electrons. And again, when you draw those Lewis structures, that basically means you're going to have one dot on one side, and then you rotate to the next side and put your second dot on the next side. So again, it doesn't really matter if you start on the top or if you start on the right or if you start on the bottom or if you start on the left. You just pick a side of the element symbol, you put a dot there, then you move to the next side and you put a dot there, and then you only have 2 solo dots that are 90 degrees from each other. That's what matters when you draw these Lewis structures. Alkaline earth metals are not as soft as alkali metals, but they are still fairly soft for a metal. You would need like an actual like steel knife to cut one of these, but it's still like pretty soft for a metal. And then they are reactive, but not as reactive as alkali metals either. They react with water at high temperatures. So if you're boiling the water, then it might explode with the water. But also that's like a really terrible idea, because then you've got an explosion where boiling water is spraying everywhere. That's how you kill people. So don't try it at home, even if you could get your hands on an alkaline earth metal in pure form, which I don't think you could. But, you know, definitely not a try this at home scenario. Group 7, all the way on the other end of the periodic table, these are your halogens. And we're back to being furious, or so angry. So with alkali metals, that one valence electron, they really want to give it away, and so they react very easily. With halogens, they have 7 valence electrons, and that means they really want to gain 1. And in gaining 1, they react very easily to just like take it from wherever they can find it. So again, when you're drawing your Lewis structure, you pick a side. It doesn't really matter which side, you just pick one. And then you put a dot, rotate, put a dot, rotate, put a dot, rotate, put a dot. As you're putting the 7 dots, what ends up happening is you should have one side of the element that only has 1 valence electron dot on it, and then the other 3 sides should all have paired electrons. We call those lone pairs. 2 electrons together on 3 sides, and then the 4th side should have just 1 electron. That's what matters about how it looks. It doesn't matter where the lonely one is, as long as you have exactly one lonely one, and then you have 3 pairs. At room temperature, fluorine and chlorine are gases, bromine's a liquid, and iodine and astatine are solids. So those are some physical properties of halogens. For chemical properties, they are always diatomic, which this is a new word. But if you kind of break it down, it shouldn't be too hard to figure out what diatomic means. It means that there are 2 atoms, 2 atoms, diatomic, 2 atoms, in pairs. So anytime you have pure fluorine, pure chlorine, pure bromine, so on and so forth, you can never have like just one fluorine atom by itself. It has to have a partner. You can never have one chlorine atom by itself. It has to have a partner of another chlorine atom. And that's true for every element in the halogen family. It has to have a partner. It can never be alone. Like you probably have a friend like that who like can never be single. Ever, like they break up with somebody and then like a week later they have a new significant other, and that's what the halogens are. Group 8 is your noble gases. They are so happy and content. Oh, so cute. Look at it. They are stable. Single and stable, that's your noble gases. They have 8 valence electrons except for helium because it's so small. It only has 2 valence electrons because it only has 2 total electrons. You can't have 8 valence if you only have 2 total, right? So helium's only got 2. So your helium is a little different. You can draw it like this. You can actually, where there's 1 dot on top and 190 degrees, you can actually also draw it with the 2 dots paired and then all the other sides empty. And that's like a special thing you can only do for helium because helium only has 2 electrons. They're both in the 1s orbital, so they technically are paired with each other. Helium's the only element you can draw it like that, where you have the 2 electrons paired and then all the other sides are empty. Only helium gets to be like that. But for, whoops, I just minimized it on my own screen. Okay. But for all the other noble gases, you end up with a full valence shell of 8 electrons all the way around. So 2 on each side. When you draw them, technically you should go 1 on each side and then go back around for a second 1 on each side. But like, I'm never going to know if you draw it that way or not. Okay. Noble gases are odorless and colorless gases. So you may be thinking like neon's not colorless, but that's actually when they put it in those neon light tubes, they put other stuff in the tube to give it the color. And also they run electricity through it, which plasmatizes it. And it's a whole thing. Anyway, noble gases also do not react. We have a special vocabulary word for that. That means that's called inert. They do not react. That's called inert. Those are your basic families. Let's talk about atoms versus ions. An atom is a neutral element, meaning that the number of protons and the number of electrons are equal. So you have the same number of pluses and minuses. They all balance each other out, and your overall charge equals 0. But an ion is an atom that has unequal protons and electrons. So there is an overall charge. There are 2 different types of ions, cations and anions. I always have students who want to pronounce this cation like a vacation, but that is not what this word is. I always have students who want to pronounce it anion like an onion, but that is not what this word is. It is cation and anion. These are compound words, so we pronounce them as separate syllables. Metals usually lose electrons to form a positively charged ion, which we call a cation. So the number of protons ends up being greater than the number of electrons. The number of protons stays the same. So if you're going to have more protons, meaning more pluses, and that's going to be greater than your minuses, but the pluses are staying the same. The only way you can end up with more pluses without changing the pluses is you have to change the minuses. The number of electrons has to go down. We have a mnemonic device to remember which ones are the cations. So there's actually 2 you can pick from. You can think of the letter T inside the word cation as being a big old plus sign telling you, hey, I'm positive right here. Or, and this is the one my students tend to favor because it's so ridiculous, you can think about how cats are, I'm drawing a tiny little horrifying cat head. Cats are positive, huh? Pause, like P-A-W-S, positive. They have pause. They're positive. Ah? Yeah? Positive? You'll remember it because it's so stupid. Okay. Meanwhile, anions are formed when a nonmetal gains electrons to form negatively charged ions. So if there's a negative charge, that means your number of protons, your number of pluses is less than your number of minuses, your number of electrons. But the number of protons has to stay the same or else it would change elements. So if your number of protons stays the same, but you end up with more negatives, more electrons, that means that you must gain electrons. The number of electrons has to go up. Our mnemonic device for this, if you think about the word anion, and if you write it with a capital A, that little crossbar on the A is like a big old negative sign telling you, hello, I'm negative. If that doesn't work, the other option I have is that, and even though you don't pronounce it onion, everyone wants to pronounce it onion. So anions, like onions, make you cry because they're so negative. Onions, oof, don't say onions, but onions make you cry because they're so negative. And anions are also negative. And sometimes they make you cry. All kinds of stuff makes me cry. Okay, let's talk about ions with respect to each family. To get a full octet, meaning to look like a noble gas, which is what every element wants to do, because the noble gases are like so cool, and they're so stable. They want to be stable, look like a noble gas. They want to get a full octet. Every element wants to have a full octet to be stable like a noble gas. And so to do that, they want to end up with 8 valence electrons. And your atoms will lose or gain electrons, whatever is easier, in order to get that full octet. It's sort of like, you know that song, I wish that I could be like the cool kids, because all the cool kids, they seem to get it. Are you too young to know that song? I don't even know anymore. But that song, the noble gases are like the cool kids, and all the other elements want to look like those cool kid noble gases. And so they will lose and gain electrons so that they can look like those noble gases. So the alkali metals, for instance, will lose 1 electron in order to look like the cool kids. They have that 1 valence electron that's just hanging out there, and they're going to lose it so that they can look like the cool kids, the noble gases. So if we think about an atom of sodium, which is drawn here, versus what an ion of sodium does. An atom of sodium has 11 protons, which I know from looking at the periodic table. And an atom of sodium is neutral, so if there are 11 protons, there must also be 11 electrons. An ion of sodium still has to have 11 protons, because if the number of protons changed, then it would not be sodium anymore. So it's still got 11 protons, but it loses 1 electron. And that means that there's a leftover plus that's not being balanced out by a minus. So that leftover plus gives it a +1 ionic charge. And if it has a +1 charge, then that tells you it is a cation, because cations are positive. That can also tell me about the ionic radius. If it's losing an electron, then the radius of the ion is going to be smaller than the radius of the atom because of losing the electrons. When you lose something, you get smaller. If we look at this model of the sodium atom, losing that 1 electron right there, that valence electron loses that whole shell. So the whole shell disappears, and it's like way smaller radius than it was before. You've lost a whole layer. Alkaline earth metals, such as magnesium, will lose 2 valence electrons. So there's 2 valence electrons that they will lose. And again, that makes this whole shell around the outside disappear. So we're going to come back to how that changes things. An atom of magnesium versus an ion of magnesium, both the atom and the ion have 12 protons. I know they both have 12 protons because the periodic table tells me so. I know that ion keeps the 12 protons because if it didn't keep 12 protons, it would not be magnesium. An atom of magnesium has equal protons and electrons. So I'm going to draw that there are 12 electrons to go with the 12 protons. But if I look at an ion of magnesium, it has lost 2 electrons. And in losing 2 electrons, it now only has 10. And that means that there are 2 protons of magnesium that are not balanced out by a negative electron. So you have 2 leftover pluses, and those contribute to a positive 2 charge on a magnesium ion. So what kind of ion is it that has a positive 2 charge? That's going to be a cation. And we know that the radius gets smaller because, again, when we lost those 2 electrons, we lost an entire shell. That makes the whole thing way smaller. We lost a whole layer. When we talk about the halogens, group 7, we can see this fluorine atom that we have a model of here has 1 unpaired electron, and that electron really wants a partner really bad. So a halogen will just take an electron from wherever it can get it and gain 1 electron to balance that out. So where a fluorine atom has 9 protons and a fluorine ion has 9 protons, in the atom, those 9 protons are balanced by 9 electrons. Pluses and minuses have to be equal in a neutral atom. But in the ion, we have gained 1 electron. So instead of 9 electrons, there's a 10th one in fluorine. And that 10th electron contributes to a -1 charge because it's not balanced out by a proton. What kind of ion has a negative charge? An anion. And what does that do to the radius? Well, when you gain stuff, it gets bigger. Because we've gained an electron, it actually ends up pushing the whole shell to be just a little bit larger and a little bit wider. Because those electrons in the shell are repelling each other. They're actually pushing each other a little bit further apart. That brings us to neon and the noble gases. They lose and gain no electrons because they're already stable. They already are the cool kids. They don't have to change themselves at all. For neon, an atom, and this time I'm not going to draw all the pluses and minuses because for neon, it's so simple. There are 10 protons and there are 10 electrons and they balance each other out. So the ionic charge is 0. And what kind of ion is it? It's not an ion. There's no charge. It's neutral. So the ionic radius, you could just say it stays the same because there are the same number of electrons. Let's talk about writing ion symbols. Remember that when an atom loses or gains electrons, the atom changes both size and charge. At this point, it is no longer a neutral atom. It is now an ion. And we don't call it an atom anymore. We call it an ion. To write an ion symbol, there are some steps. First, you write the symbol for the element from the periodic table. Then you check the charge for that family or group. You write the ion's charge to the upper right after the symbol as a superscript. So it ends up looking like an exponent. But you do have to write the positive or negative sign. In your math class, numbers without a positive or negative written there are always assumed to be positive. You don't get to assume that in chemistry. If the charge is positive, you have to write a plus sign for the charge. And if it's negative, you definitely have to write the negative sign for the charge. So there are several practice problems here. I'm not going to do all of them here in the video, but for lithium, the atom symbol for lithium is Li. If you look, lithium on your periodic table is in group 1, which makes it an alkali metal, and the alkali metals have a +1 charge. So I'm going to give it a +1 charge, and the ion symbol would be Li, and then up to the right at the top like an exponent, I write +1 for a +1 charge. You actually, when there's a 1, you don't have to write the 1. You do have to write positives, but you don't have to write 1s. So you could also just write Li plus and leave the 1 off. It's a little different than your math class. You know, we're like funky here in chemistry where we change some rules. Beryllium, similarly, Be, if you look at the periodic table, beryllium is in your alkaline earth metal family. All the alkaline earth metals have a +2 charge. And so your ion symbol for beryllium is a Be. And then up at the top, like an exponent, you can write +2. You actually also could write Be2+. Either of those is correct. So I know in your math class, the plus sign has to go before the number. In a chemistry class, it can go before or after. And then the other one I'm going to do right now is fluorine. If you look at your periodic table, fluorine is a halogen, so it's got a -1 charge. All the halogens have a -1 charge. And you can, again, you can write that as F, and then like an exponent, you can put -1. You could also write that as F1-, or you can leave the 1 off entirely and just put F-. All of those are considered correct in chemistry. For atomic radius, the size of a neutral atom is the atomic radius versus an ionic radius is the size of an ion. So it has lost or gained electrons, and it will get smaller if it loses electrons or bigger if it gains electrons compared to a normal atom. So for instance, lithium will lose 1 electron to get a full octet. It'll lose that valence electron on the outside. The symbol for an ion of lithium would be Li with a +1 to the top right, written like an exponent. For the ionic radius, that whole outer shell comes off, and then you can see that it is smaller because it lost electrons. For beryllium, we know that the 2 outer electrons, both valence electrons, get lost. We know that because beryllium is an alkaline earth metal, and alkaline earth metals all lose 2 electrons. You can tell by finding it on your periodic table. It is in group 2. It's an alkaline earth metal. All alkaline earth metals lose 2 electrons when they become an ion. That tells me that the beryllium ion is actually beryllium with a +2 charge. It has lost 2 negatives. So it had a 0 charge when it was an atom, then it loses, so subtracts 2 electrons, but those electrons are negative. So you're really doing 0 minus -2 on the charge, which gives it a +2 charge overall. Because those 2 valence electrons disappeared and a whole shell disappeared, that leaves us with a much smaller atom than before. We've lost the entire outer shell. And because of that, we have a smaller ionic radius from losing 2 electrons. We have a chlorine example here where we can see that chlorine has 1 little lonely electron that needs a partner. So it's actually going to gain an electron like all of the halogens would. If you check your periodic table, chlorine is in group 7. It's a halogen. It will gain an electron. So it's going to gain 1 electron. And what that does to the charge is chlorine starts with a 0 charge when it's a neutral atom, but then it gains, so it adds on 1 electron. But that 1 electron it's adding on is negative. So you're actually doing a 0 charge plus a -1 charge. Overall, that's going to give it a -1 charge. When we think about what that chlorine ion does, we end up having like the first shell was full with 2 electrons, the second shell was full with 8 electrons, and now we have a third shell that is full with 8 electrons. And those electrons are all repelling each other because opposite charges, or excuse me, like charges repel. They push each other to be bigger and further apart. So having gained an electron actually makes this whole atom bigger because it gained 1 electron. The last thing I'm going to talk about in this video is how to compare the size of an atom to its ion without actually having to draw it. So this is how a grown-up chemist would do it. Drawing atoms and ions, like I just did on the previous page, can take a while. How can we know if the ionic radius is bigger or smaller without having to draw the whole thing? Drawing it out is so basic. So let's think our way through it. We can have questions like, which is larger, sodium or sodium plus 1? It helps to recognize that the one with no charge is the atom, and the plus 1 charge tells me that one is the ion. The sodium atom, to become the ion, has to either gain or lose an electron. To answer that question, does it gain or lose? Look at your periodic table. Sodium's an alkali metal, and according to your notes, alkali metals lose 1 electron. So the sodium atom loses 1 electron, and then it will become an ion with, and if you look at your notes, alkali metals have a plus 1 charge. When it loses that 1 electron, it will get smaller. When it loses, it gets smaller, right? Losing stuff makes you smaller. So the sodium atom or ion is larger than the sodium atom or ion. That's the last thing we're answering here. Which one is larger? Well, the atom starts off with some electrons. After it loses, it gets smaller. So the ion is smaller because it lost. And that means which one is larger must be the atom. The atom is larger than the ion. Next example, which is larger, fluorine or the F- ion? Again, notice the neutral one is the atom. The one with the charge is the ion. The fluorine atom has to lose or gain an electron to become the ion with the charge. Well, we can look, and the charge is written for us right there, -1. I know that the family with the -1 charge is the halogens. And if I look at my notes, all of the halogens, when they become ions, they gain an electron. So I'm going to recognize that because fluorine is a halogen, it gains 1 electron to get that -1 charge. So when it gains the 1 electron, it's going to get bigger or smaller. Gaining makes you bigger. So if the ion has gained and the ion is bigger, then the fluorine ion is larger than the fluorine atom. Final couple examples, which is smaller, magnesium or the magnesium plus 2 ion. Again, recognize that magnesium with no charge is an atom. Magnesium with the charge is an ion. If you think about it, magnesium has to lose electrons to become the magnesium plus 2 ion. The ion then has lost electrons, and that tells me the ion is smaller. So when they ask, this makes which one smaller than the other? The ion is smaller than the atom. And our final example, which is smaller, bromine or the Br-1 ion. Again, the one with no charge is the atom, and the one with the charge is the ion. If we think about it, bromine, to become bromine-1, has to gain electrons. Bromine, if you check, is a halogen. All the halogens gain an electron to get a -1 charge. And that means that if the ion has gained, the ion is bigger, and they are asking which is smaller, so the atom is smaller than the ion for bromine. There are some example problems here in this chart. I'm going to just do one. Magnesium is an alkaline earth metal, which I know because if I look at the periodic table, it is in group 2. Group 2 is called the alkaline earth metals. If you look at your periodic table on top, there's these tiny little numbers printed on this 1, this 2, over here, 3, 4, 5, 6. Those are the number of valence electrons. All of the alkaline earth metals have 2 valence electrons. Magnesium, to look like a noble gas, is it going to lose or gain electrons, and how many? I know that since it's an alkaline earth metal, it's going to lose 2 electrons to look like a noble gas. The ion symbol, when it has lost 2 electrons, the charge was 0, then it loses, so subtracts 2 electrons, and electrons are negative. So the charge is 0 minus -2. That gives it a +2 charge. And that means, oh, this asks for the ion symbol. So that means your ion symbol is Mg for magnesium with a +2 charge written up top right like an exponent. And then is the ionic or atomic radius larger or smaller. The ionic radius will be smaller because it has lost electrons. Okay, that is where I'm ending this video. Good luck and enjoy.